So before we jump into math and calculations and the theory of gases, I want to get our minds really into thinking about how we could define, measure, quantify gases. We're going to have a bit of a discussion, and then we'll just summarize these on the board. Some of your ideas or some of the things we're going to talk about, we're not going to study in this course, but I want to highlight those key variables that we are going to define and come up with relationships that relate one to another. So we discuss, I'm just going to use their symbol, so volume was where we just finished our started our brainstorming discussion. Pressure came up. Okay. Temperature is definitely something that's going to be very important. If you change the temperature of gases, you can change the volume or change the pressure. Okay. Density is something, how heavy it is per unit volume. And part of density, which is mass per volume, is mass, is something that you could measure with a gas. And then as chemists, we're going to be doing that mass to mole conversion. Color of solutions is something we're definitely going to study. Color of flames is something we'll look at in a future unit. Okay. But gases could have colors. We just want to address that right now. Okay. One thing that didn't come up in the brainstorming we just did was what kind of gas you put in or what mixture of gas you put in is certainly something that's going to affect some calculations. Okay. So the fact that there's oxygen in won't change things sort of just by the fact of the type, but you need to know the kind to know what molar mass you would need to calculate in terms of ultimately studying the gas. You know, you need molar mass and mass to ultimately get to moles. That relationship's going to come up again. Okay. So we're going to get started on the next slide, talking about pressure and talking about temperatures where we're going to begin. And then in the next lesson, we're going to get into some of the gas laws that relate volume to pressure or temperature. Different gas laws relate different 2 or 3 of those variables that I have starred. So pressure first, temperature second. So what is pressure? I'm never going to test you on this, but conceptually you need to be comfortable with what is pressure. It's the force exerted on a given area. So in a balloon that's pushing out in the plastic, there's a certain force of the molecules pushing out on the balloon, and you'd measure that by a force divided by a certain area, maybe a square centimeter, a square meter. Now, in terms of the standard unit, it ends up coming out to be really small. If you use SI units, you end up with newtons as the SI for force over meters. And that combination of units, Newton divided by a meter squared, is a Pascal of pressure. If anybody's ever paid attention to the weather, some only care about the temperature, but if you listen to the pressure, they would give the forecast and how many kilopascals or thousands of pascals the pressure is on a given day. And you mostly care about, if you listen to weather, whether the pressure is going up or going down. That tells you something about how the weather is changing. Okay. We're going to be using non-SI units. Okay. Large, Pascal just doesn't work. It's too small. So some of the units that we're going to be using, and we need to learn how to convert between, is kilopascals, the ones used by Environment Canada. We're going to be using atmospheres, where 1 unit or 1 atmosphere is typical pressure at sea level. That's where that unit came from. And then one of the oldest units is millimeters of mercury or torr. They both are for the same unit. They're just a different name. Torr is named after a scientist. Millimeters of mercury is literally how many millimeters mercury would push up in a vacuum at a given pressure. So I don't care if you take down this diagram. I'm not going to test you on this original barometer, but I want to, again, get your mind set into, what is pressure. And this is how the original measurements were made, how scientists figured out pressures hundreds of years ago. They'd have a big pool of mercury, and there'd be a sort of upside down test tube or tube into that pool of mercury. And the top of the test tube doesn't have any air in it. We see a gap at the top, but that's a vacuum. Okay? There's no air to push down against the mercury. Okay? So the mercury is going to want to go up this tube, up into the vacuum. But as the mercury goes up into the vacuum, just the mass of the mercury, gravity is going to want to push it back down. So the more air pressure pushes onto the pool of mercury, the higher the mercury is going to get. Okay? So the more force down by air, the higher the mercury will get until eventually gravity stops it from going up. And this was the original way, the original barometer of measuring pressure. Okay? They'd measure the millimeters that mercury went up. Okay? And that's where these units came from. At atmospheric conditions, you'd find out that mercury would go up 76 centimeters, or 760 millimeters is how high the mercury would get. So that set, 760 millimeters of mercury going up is the same as 1 atmosphere. Okay. Now in the kilopascal units, okay, the 76 centimeters corresponds to 101 and a bit kilopascals. So that's sort of the 3 conversion of units, or typical conditions for the 3. We're going to need to use these numbers to convert from one unit to another. So 1 atmosphere, 101.3 kilopascals, which is that 760 torr, and torr in millimeters of mercury are the same. The millimeters of mercury got renamed in the honor of a scientist. So I'm about to do a couple examples of converting one unit to another. Okay. I'm going to take the given data, whatever units, maybe we have 800 torr that we want to convert. That would be our given data. I'm going to multiply by the required unit conversion and divide by the given unit conversion. So what's in green is sometimes called a unit ratio. It's where the top and the bottom are equivalent to each other. They have the same meaning, but they're in different units. Okay? It's similar to the factor label method from Science 10. Okay? Now, when I say equivalent to each other, in math, you might see something like 100 centimeters is equal to, well, 100 centimeters is 1 meter is 1,000 centimeters, sorry, keeping more common units. 1,000 centimeters, 1 meter, they mean the same thing, and you'd see something like that go into a unit ratio to convert. Okay, we're going to be putting 2 of those 4 conversions up above. So if we wanted to convert 2 atmospheres, we'd take the given conversion, put it on the top, and would put the atmosphere conversion on the bottom, and we would convert it. Okay. So I'm going to use this method to convert about 1/3 of an atmosphere to millimeters of mercury. So I've already typed out the given data, that close to 1/3 of an atmosphere. The required unit conversion goes on the top. So I want millimeters of mercury, and I'm actually going to put those units in first. I'm going to organize this before I get the numbers. The units I want to get rid of are atmospheres, so they're going to go on the bottom. So you don't even really have to remember that required over given. It's the same language that's used in STOIC. Okay. Units you want to get rid of go on the bottom, so they cancel. The units you want go on the top, and then we got to grab those unit conversions. Now you're going to have a formula sheet. You're not memorizing these. You're just going to your formula sheet and grabbing these numbers. So it's 760 millimeters of mercury is equivalent to 1 atmosphere. My atmospheres on the top cancel my atmospheres on the bottom. The only units left are the units I want, and then you grab your calculator and do the arithmetic. And I get 252 millimeters of mercury. Now our original data had 3 sig figs. The 760, all 3 of those, you wouldn't be maybe sure whether this 0 is significant, but those 3 digits were all measured, even though that end one is a 0. And our 1.00 has 3 sig figs, so that's why I rounded the way I did. Okay. So I'm going to do 2 more examples, and then you're going to do 2 examples for me, and then we'll move on to temperature. So the first example I'm going to do is convert 0.9 atmospheres to torr, and then in B, I'll convert it to kilopascals, and then I'll put up 2 examples for you to do. So you always start with your given pressure. Okay. And we're doing this because we often have to match units, and certain formulas have mandatory units to use them. Okay, so just like you might have to use liters in a formula, and I might give you milliliters, you might have to use kilopascals in a formula, and I might give you atmospheres. You have to be able to interconvert pressure units. So 0.9 atmospheres, I'm asked to get it to torr, and I want to get rid of the atmosphere units. So I have the required units on the top, the given on the bottom. I go to my conversions. 760 torr is 1 atmosphere. It's really kind of the same as what we just did, because torr and millimeters of mercury are synonyms. Atmosphere, atmosphere. Now in this case, there were only 2 significant figures in our original information. So I'm going to have to round to 2. So I have rounded this to 680 torr. With the 6 is measured, and then the 8 got rounded. Those are 2 sig figs. The N0 is just a placeholder in the 1 spot. I'm going to do this all over again, but I'm going to turn it to kilopascals. So 0.9 atmospheres, which is very close to what you would see here in Calgary, Alberta. Vancouver, you'd be around 1 atmosphere. We're about 10% lower. I want kilopascals this time. I want to get rid of atmospheres. 101.325 kilopascals is exactly 1 atmosphere. Okay. We're starting with that same 0.90 with 2 sig figs. So I'm going to keep 2 sig figs. So the 10s in ones place is all I need. So 91 kilopascals. Okay. Now, as an aside, it is a bit confusing. If you ever hear the forecast, you won't hear them say 91 kilopascals. They take the pressure that we are in Calgary, Alberta at elevation, and they recalibrate it down to if it was at sea level. So everywhere across the continent, they adjust out the altitude of the pressure, and it helps them compare pressures in different areas to make their weather maps. So I'd like you to convert A, 95 kilopascals to atmospheres, and in B, 811 torr to atmospheres. Okay. We'll give hopefully about a minute to a minute and a half will be enough to go through these two in more detail. So for the first one, there are 1, 2 sig figs in the given information. So that's going to limit our answer. So I rounded it to 9.94 atmospheres. I had 0.93757 that I rounded. The bottom one, we have 3 measured digits, and we have 3 or more in all our conversions. So 1.07 atmospheres is what I got for the second one. Okay. So that's pressure. We're going to leave pressure a little bit. We're going to talk about temperature, or sort of all of them a little bit. Before we do our temperature conversions, we're going to talk a little bit about standard conditions that talk about temperature and pressure. In gases, the conditions can change really easily. Okay? When we're dealing with solutions or mass, the mass doesn't change its volume, it just stays put. Okay? Solutions tend to stay in their container, but gases will vary their pressure, their temperature, their volume. They can all change really easily. Or you could run experiments under slightly different conditions, which doesn't make it easy for somebody to compare their experiment done in Calgary to Vancouver to South Africa to Japan. So chemists have come up with standard conditions that we can all try to mimic so we can compare our results. The slightly older standard is called STP, Standard Temperature and Pressure, which you have on your formula sheet, which is 0, 1 atmosphere, so a little over 100 kilopascals is standard conditions. Now, those aren't great conditions. Imagine you're in the lab under those conditions. You're kind of a little chilly, right? And that would be hard. Like, you'd have to pay for refrigeration. You know, if you do your experiment in, let's say, a pool of water or in a container, you'd have to cool that container down. and that's more difficult. It's actually a lot easier to do standard ambient temperature and pressure. There's an A added in. We've increased the temperature, this is a bullet, not a minus, to 25 degrees Celsius and 100 kilopascals. All my university labs, or the thermodynamics ones, were done at 25 and close to 100. To get this, you're going to be surprised. You're going to go into a lot of university physics labs or chemistry labs and be like, why do they have a fish tank? There's no fish in those fish tanks. The fish tanks have a heater, and the tank is heated to 25 degrees Celsius. And you can take your chemicals and vials and put them into the top of the fish tank, and this water at 25 keeps the vial and all your chemicals at 25. Okay? And so it's not that hard to run an experiment under standard conditions. Okay? A slight heating. So you need to be aware of these conditions. If a question says this reaction occurs under SATP, I am coding, telling you both the pressure and the temperature of that reaction. Okay? And you need to go to your sheet and look it up. Okay? Also, as we work our way through chemistry and you use the Alberta 2030 data booklet, almost every value in here is under standard ambient temperature and pressure. It's just how scientists build data tables. So we're going to discuss temperature now a little more thoroughly. It's something you think you know a lot about, but we're going to sort of do the science side, and we're going to have to not use Celsius. We have to use a different scale because Celsius was just randomly chosen with a 0, and that's not going to work for us, a scale that has a random 0 number to it. Okay, so ultimately, what is temperature? Well, the colder something is, the less the particles are moving. The hotter something gets, the more the particles start vibrating. It's not translational motion, it's vibrational back and forth. So fast, it's vibrating a lot. High kinetic energy slows down. As the temperature goes down, it slows down. Okay. And in the AP part of this course, we'll actually learn that it can't slow down and stop because that would violate a principle of science called the Heisenberg uncertainty principle. So we'll dive into that again in the AP in the quantum mechanics section. So against what you'd guess, you'd think 0 temperature would be absolute stop, but 0 temperature's almost stopped. You can measure temperature in a relative scale Celsius, but we're always going to have to convert it to an absolute scale, which is called Kelvin. And we're going to spend most of this slide learning about the Kelvin scale. Kelvin is where our 0 is the bottom, is our coldest possible temperature. All of our gas law measurements have to be done with absolute scales, which will make sense when I make the following comment. If your scale for pressure has to be, well, 0 pressure is no pressure. 0 volume is no volume. Okay? But 0 Celsius is not no kinetic energy because you can go negative a whole bunch. So we need a temperature scale where 0 on our temperature is as low as you can get. And that's what Kelvin does for us. So we have degree Celsius or Kelvin. There's no degree to the Kelvin scale. Okay. Now it turns out that when it's 0 outside and you think it's cold, oh, it could get a lot worse. We're at 273 and a bit Kelvin. Okay. So we're a long, long way up from 0. Okay. Now the way Kelvin has been set up is 1 degree Celsius, or particularly the change in 1 degree Celsius, is equivalent to 1 Kelvin unit. Okay? So the units have the same meaning, or the same sort of difference. Like Celsius and Kelvin, or degree Celsius and Kelvin, you know, one Fahrenheit change isn't 1 degree Celsius change. Okay? a degree Celsius is way more than a Kelvin unit, or way more than a Fahrenheit unit. But here it's the same. If you go up 10 degrees Celsius, you go up 10 Kelvin. You go down 10 degrees Celsius, you go down 10 Kelvin. So if 0 degrees Celsius is 273 Kelvin, that Kelvin could go down to 0. It'd have to go down 273. So the Celsius could go down 273 before it would hit the bottom and couldn't get any colder. So I want to look at, I need to get your brains rewired a little bit from the Celsius scale that you're used to into the Kelvin scale, and I'm going to do that with a vertical number line. You're kind of used to thermometers going up and down, so I think it makes sense to do this number line vertically as opposed to horizontally, where you do number lines most of the time. So I've got my number line set up. I'm going to start with that 0, 273. So I'm going to put degrees Kelvin on the left, degrees Celsius on the left and Kelvin on the right. So 0. I'm going to leave out the decimal places to have a cleaner number line. So I'm not going to be putting in the 0.15. I'm dropping it. I'm dropping down to 2 sig figs. So let's go up first. So the whole Celsius scale came from the freezing point of water. The boiling point of water was set as 100. And you get kind of one of the original names, centigrade, centa, 100. Okay? So they just took water freezing, water boiling, and broke it into 100 pieces, centigrade. Which later got Celsius's name as the scientist who worked on some of this, had his name put onto it. He didn't fully develop this scale. On the Kelvin scale, if we're up 100 Celsius units, would be up 100 Kelvin units. So that's 373 Kelvin. We're going to go down as far as we possibly can go. Okay. How far down can we go? Well, 0, the very lowest amount of kinetic energy we can possibly have. Okay. This is sometimes called absolute 0. As a scientist, you can't go below this. It would have no meaning. It'd be like you can't go past something pretty much stopping. Okay. Star Trek might have antimatter, but we don't go below 0. We don't have anti-motion or things like that. Now on the degree Celsius scale, how far can we go down? What is absolute 0? Well, we went down 273 here. We've got to go down 273 here. So we're negative 273. That's our coldest day benchmark. So the next day that's minus 35 and somebody says it's really cold, you go, well, it can get a lot worse. Could be minus 100. Could be minus 200. And then they go, ha, I'll beat you. It could be minus 300. You'll go, no, that makes no sense. We can't go to minus 300. 273 is the coldest it could possibly be. There's no minus 300 possible. Okay? The same way you can't have a volume of minus 1 liter. Okay? Does it almost hurt the brain? Like it just would make no sense. It's like it gets smaller, 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 and implodes into itself. It's in another universe or something. I don't know. You can't have negative numbers to absolute type value scales. Okay. So that sets our bottom. Now, there's kind of 2 ways to do the conversion. I do it by kind of just figuring it out. There's always a 273 difference between the two. Okay? And then I just remember that the Kelvin is always the bigger one. And then I figure out whether I need to add or subtract. So that can work. If you remember that Kelvin is always bigger and 273 is your conversion, you can just deduce it. If you like a formula, which you don't get, you'd have to memorize it. You can get Kelvin by taking degrees Celsius, and you always add 273, which makes it the bigger of the two. Or if you want degrees Celsius, you take Kelvin and you subtract 273. So either memorize these formulas or deduce them, remembering Kelvin is always the bigger one, and then remember whether you add or subtract. Okay. So I'm not going to do any examples. So just be either adding or subtracting 273. I'm going to have you jump right into some problems. So I have 5 or 6 that I'd like you to work through. Okay. Now, don't bother with the decimal points, just do your answers to the ones place. So I'm going to start with 3000 Kelvin. What is that in degrees Celsius? 500 degrees Celsius. What is that in Kelvin? Minus 25 degrees Celsius. Convert that one to Kelvin. 100 Kelvin to degrees Celsius, and last 2000 degrees Celsius. That one to Kelvin units. And we'll recap those answers after you've had maybe about 3 minutes to work through those. Okay, so let's recap the answers. The first one is Kelvin to Celsius. Kelvin is the bigger number, so we have to subtract to get to degrees Celsius. So 2727 degrees Celsius. Our second question, we're going to Kelvin, which is the bigger scale, so we have to add in this case. So 773. The next one is also degrees Celsius to Kelvin, which is bigger, so we're adding 273. You just have to watch your integers. You got a negative number, and then you're adding to it. 248 Kelvin. Kelvin to the smaller degrees Celsius, 100 Kelvin, which is pretty cold, way colder than it's ever been on our planet. We subtract 273, so we get 173. And 2000 degrees Celsius to the bigger Kelvin, so we add 273. So hopefully you're able to get through those 5 conversions. As a big warning, there's definitely going to be errors made with this. Never use degrees Celsius in calculations. The question might give you degrees Celsius. I may ask you for the answer in degrees Celsius, but you can't use it for your math. You're going to get, you're going to get garbage out. You're going to have these negative numbers put in. You might have 0 degrees Celsius, which will give you undefined. You might end up dividing by temperature. It just doesn't work. You need an absolute scale. And this is something that it's easy to miss if you're in a hurry and you just think of the formula and you plug in the numbers. Last slide, you don't even have to put this in your notes. You could just sit back and watch. It's more of a theory, not something I'd test you on. Okay. How on earth did we find out this absolute 0? It's really cold. It's not easy to get there. We do have technology now that we can get there. Helium will condense at 4 Kelvin, and we can get refrigeration cold enough to take helium and turn it into a liquid. But it's really expensive and really difficult, okay, to get that low temperature-wise, okay? But we have figured out, calculated what absolute 0 is through extrapolation. Experiments were done with gases in certain volumes, and they kept cooling the gas. So here's our temperature scale on the X. We got volume, so imagine this balloon. Okay. And I haven't even taught you any gas laws, but you know, if a balloon gets colder, does it get bigger or smaller? It gets smaller. Okay, the particles are moving slower, so they hit the wall with less force, and there's less pressure, and the atmosphere squeezes it. So as you cool this down, it's going to get smaller. And that's kind of what they did. You know, here's the highest temperature, they measured its volume. They cooled it down, they measured its volume. They cooled it down, they measured its volume. They collected a bunch of data, and then they extrapolated it. What is the trend? What temperature would be required to get this balloon to go to no volume? And it turns out when you extrapolate to what temperature would get this down to 0 volume, it's of 273. Now that worked with one gas, and then they've redone this experiment with all kinds of different gases, where the blue, the orange, and the red represent different gases. And it doesn't matter what gas they pick. When they extrapolate it out, they keep getting this 273 number. So it's scientific investigations combined with extrapolation, okay? And you can do this with temperature and pressure. Also, this 273 is where everything keeps correlating to or trending to. So that's where we've figured out, predicted what absolute zero would be. Even though it's not a temperature, we can get a box down that cold. Again, 1, 2 Kelvin, maybe in the range of doable, okay? Right down to 0 is not.